Hello everyone, myself Cam Rupnevar from TC College Baramati, and I'm going to start a new topic from chapter number 5, fluorescence and phosphorescence. The today's topic is electronic transitions during photoluminescence. As we have already studied the fluorescence and the phosphorescence. The photoluminescence types are fluorescence and phosphorescence. The fluorescence occurs when the transition occurs from singlet state S0 to the excited singlet state S1, and the phosphorescence occurs when the transition is from ground state singlet S0 to the excited state S1, and then the intersystem crossing occurs to the triplet state, and there is a vibrational relaxation, and after that the species come to the ground state with the emission of light. This is called as a phosphorescence. The electronic transitions during photoluminescence are the pi to pi star transition and N2 Pi Star Transition. Fluorescence and phosphorescence in most cases preceded by absorption and subsequent relaxation to give a molecule in the first excited singlet state. The S0 to S1 transition is most important in determining the extent and the type of luminescence that occur. When transition occurs from S0 to S1 and then there is a relaxation, the process is known as a fluorescence. And when transition occurs from S0 to S1 and then there is intersystem crossing, the molecule or the species come to the triplet state and then comes to the ground state. This is the phosphorescence. There are main two types of transition occurs, pi to pi star and N2 Pi Star transitions. This is a diagram of electronic transitions. This diagram is useful for the transitions in the ultraviolet and the visible region. The valence electron takes part in the transitions, and here on the y-axis energy is noted, and here 5 types of orbitals are arranged according to their increasing energy. First one is a bonding molecular orbital. There are 2 types of bonding molecular orbitals, sigma and the pi. Then non-bonding molecular orbital is n, and after that anti-bonding molecular orbitals pi star and sigma star. The energy required for transition sigma to sigma star is much higher, and in case of fluorescence and phosphorescence this transitions is invisible. So, remaining 2 transitions, pi to pi star and N2 Pi Star transitions are possible in case of the fluorescence and the phosphorescence. See here, the pi is the bonding molecular orbital and the transition occurs from pi to pi star. Pi star is an anti-bonding molecular orbital. The energy required for transition pi to pi star is greater. Pi is a ground state orbital and its energy is less as compared to the n. Then next transition is N2 Pi Star transition. N means non-bonding molecular orbital. The transition occurs from non-bonding orbital to the anti-bonding orbital N2 Pi Star, and this orbital is of higher energy as compared to pi. So these 2 transitions are most important to study, fluorescence and phosphorescence. When pi to pi star transition occurs, molecule is initially in the ground state pi, it goes to the excited state and then comes to the ground state with emission of light. This is called as a fluorescence. And the next transition is N2 Pi Star transition, where the molecule is in the non-bonding molecular orbital or the electron is in the non-bonding orbital and it goes to the excited state pi star. Then it comes to the triplet state and then there is a relaxation from pi star to the pi, and this is called as a phosphorescence. Time required for N2 Pi Star transition is greater as compared to the fluorescence transitions. Here I have taken an example of acetone, or this is also called as a propanol. Here same diagram as previous. The bonding orbital is pi, non-bonding orbital is n, and the anti-bonding orbital is a pi star. And pi star is a bonding orbital. There is a transition from pi to pi star, and the energy difference between pi and pi star is larger as compared to the energy difference between N2 pi star transition. See here, C double bond O. This double bond includes pi bond and pi bonding orbital for C double bond O, showing constructing overlap of p orbitals. And next one is a non-bonding electrons, where there are two lone pairs present on the oxygen, and this lone pairs means there is a unpaired electrons, and this electron takes part in the transition. This is called as a non-bonding orbital to the anti-bonding orbital transition. This N is a non-bonding orbital. And next one is a pi star. Pi star is an anti-bonding orbital, and which shows the destructive overlap of p orbitals. The electrons in the non-bonding orbital are higher energy than the electrons in the bonding pi orbital. The transition from the non-bonding orbital N to the empty pi star orbital requires less energy than the transition from the bonding pi orbital to the pi star orbital. Means the energy required for transition pi to pi star is greater as compared to N2 pi star transition, and obviously lambda max values are different for these two transitions. Then this is a Jablonski diagram which shows the electronic transitions. See, here is the ground state, ground singlet state. This is the excited singlet state, and this is the next excited singlet state, S0, S1 and S2. A molecule is initially present in the ground state, S0. It goes to the excited state. Now we have to consider only S0 and S1 state. So I am considering transition from S0 to S1, and when there is a relaxation in few seconds, this process is called as a fluorescence. Singlet to singlet excited state, and then relaxation to the ground state singlet with emission of light. This is called as a fluorescence. And when the transition occurs from S0 to S1, and then there is a intersystem crossing to the triplet state, and time required for intersystem crossing is 10 to minus 10 to 10 to minus 8 seconds. There is a vibrational relaxation in the triplet state, and then there is a relaxation to the ground state singlet S0 with emission of certain amount of light. This is called as a phosphorescence. Means phosphorescence involves S0 to S1 transition, S1 to triplet by intersystem crossing, and then vibrational relaxation is there, and then the species come to the ground state with emission of light. This is a phosphorescence. And now the first transition is pi to pi star transition. Pi to pi star transition is observed in the double bond containing compounds. For example, aromatic compounds and the conjugated organic dyes. That do not contain heteroatom. When there is a heteroatom, obviously N2 pi star transition is possible. So that consider aromatic compound or a conjugated organic dye in which oxygen, nitrogen or sulfur is absent, and the compound which shows pi to pi star transition whose molar absorptivity is nearly equal to 10,000, and it indicates that the transition is highly probable. And it favors fluorescence because the amount of absorbed radiation I0 minus I is increased in equation. Intensity of luminescent light is equal to phi in a bracket I0 minus I. Phi is a quantum yield. IL means intensity of luminescent light, I0 means intensity of the absorbed radiations, and I is the transmitted radiation intensity. Hydrocarbons that luminance always involves a pi to pi star transition because non-bonding molecular orbitals are unavailable. And next transition is N2 pi star transition. N2 pi star transition means non-bonding molecular orbital to the anti-bonding pi star orbital. There is a transition. An example of this type of transition is the heteroatom with as oxygen, sulfur and nitrogen, and the heteroatom present in a molecule or in a compound. It's an example of N2 Pi Star transition because heteroatom like nitrogen, sulfur or oxygen contains a lone pair of electron, and this electron takes part in the transition to the highest excited state pi star. And the transition occurs from S0 to S1. S0 is a ground singlet state and S1 is a excited singlet state, and this transition is called as a N2 Pi Star transition when there is a heteroatom exists in a luminescent molecule. An electron in a non-bonding orbital that is associated with the heteroatom is excited to a pi star orbital of the molecule. And the molar absorptivity of such type of compounds is less than 1000 and is less than the pi to pi star transition, because in case of pi to pi star transition molar absorptivity is nearly equal to 10,000, and here the compound which shows the N2 pi star transition, the molar absorptivity is very less, which is less than 1000, and this is because of n orbitals do not overlap with pi star orbitals as much as bonding pi orbitals do, because bonding pi orbitals overlaps with the pi star but non-bonding orbitals do not overlap with pi star orbitals, and due to that molar absorptivity is reduced and less fluorescence is observed in the transition into pi star. Then the energetic difference between the first excited triplet state and the excited singlet state absorption corresponds to an N2 pi star transition and is smaller than pi to pi star transition. Means simply, as we have seen, the energy difference between N2 pi star transition is less as compared to pi to pi star transition. And the excited triplet state and the excited singlet state, that means S1 to T1, there is a less energy difference. That's why N2 pi star transition occurs and the pi to pi star transition occurs in less quantity. And N2 pi star transition shows less fluorescence because of intersystem crossing and increased phosphorescence. Emission from pi star triplet state to a pi ground state occurs. Means molecule is initially in the S0, it absorbs energy in the form of photon, it goes to the excited state S1, and then from S1 it comes to the triplet state with intersystem crossing, and in this triplet state there is a vibrational relaxation. Initially the S0 means N, S1 means pi star, and from pi star it comes to the triplet state, and from triplet state it comes to the ground state.